with Contributing Lrama. Welcome, Kobayashi Junichi.
Thank you. Hi, everyone. Today, Junichi Kobayashi from ESM, will be presenting on the topic, Understanding Parser Generators Surrounding Ruby with Contributing Lrama. Thank you for your taking time to my presentation. Now, let me begin with a brief introduction. Oh, my God. Name is Junichi Kobayashi, and you might find me on X and GitHub under username junk612. And I'm a lazy engineer at ESM, working in the Ruby Agile group within the Agile division. In terms of hobbies, I have keen interest in parsers and also enjoy gaming. I often play rhythm games and also, excuse me, I often play rhythm games and situation games and tabletop games. Additionally, I engage in speed cubing. Let me tell you a bit. Sorry. Let me tell you a bit about my company, ESM. ESM is an IT development company in Japan. Today, there are 4 of us from ESM attending, including myself. The company has generously covered all our travel and accommodation expenses, and it's listed as a speaker sponsor for this event. By the way, the name ESM stands for the initials of A System Management, which is the company's name in Japan, as you can see written in Japanese in the slide. Yes, it's Let me briefly explain for those who might not be familiar. There's a distinct yui-knk right next to type SD, and it shares the same kanji as Eiwa in our company's name. So, having arrived in Taiwan yesterday, I immediately made my way here. It seems that Rufa night market is quite similar to the tourist spot. Also, I couldn't have spent much time there due to preparation for today's presentation. And it's a really enjoyable experience. Additionally, on my way here, I came across a shop named Yonhe Soy Milk King. So I stopped by for breakfast. So, from tourist so paid, I came from Eiwa. I visited Yonhe. I have a breakfast at Yonhe. I'm looking forward to today's session. And Ryudo-san, thank you for teaching me at the correct pronunciation. Here's the outline for today's topic. First, I decline basic knowledge of parsing, which is essential to understand this presentation. Next, I talk about my contribution to Lrama. Following that, I share insights into the international structure of Lrama that I ran through implementation. Finally, I discuss my future endeavors. Let's start some basic knowledge of. I'll be discussing for the following topics. It's too many. First, I talk about the components of parsing, which includes lexes, parsers, parser generators. Then I talk about some technical terms in the field of programming language processor, including formal language and context-free grammar and backsimple form. So let's start the components of parsing. There are programs that operate inside the programming language processor once the source code is fed into it. Complexer is a program that reads text, such as a source code, and split into tokens. Taking Ruby as an example, a class declaration follows the sequence class, string as class name, and international implementation and end. So the lecture jobs to break this down into individual parts like class name, and end. This process is known as tokenization. Next, let's talk about parsers. A parser is a program that extracts internal structures from the tokens. I use some internal structures, sorry, derivatively because its meaning varies depending on the context. In a compiler, for example, the parser takes the tokenized source code and constructs an abstract tree. It is abbreviated as SD. For however, for JSON or CSV parsers, it process differs slightly. For example, if you use JSON.parse, it returns a data structure combining arrays or hashes for JSON. And for CSV, it might return something like a CSV table. These kinds of programs are collectively referred to as parsers. And finally, I talk about parser generators. Technically, this is not components of syntax analytics itself. Each programming language has its own unique grammar, and the parser generator is a program that takes a grammar file written for a specific language as input and outputs a parser, the grammar. So the Ruby language processing system takes .rb file and executes processes within its internal VM. To show you how data is transferred through the system, I created a diagram. It illustrates the journey of data, from the initial .rb through .rb file through various stages in processing within the Ruby system, like this. The source code is processed by Alexa to create a token stream, and then it passes the parser, and parser generates an ST, and this ST is received by the generator, which converts into the bytecode. Finally, the bytecode is handed over to the VM to execute how process flows. As for the role of parser generator in this process, it is actually operated outside of this environment. The parser generator reads the language's grammar file and generates a parser, which is then used as the parser within the execution environment. By the way, here's the interesting tidbit. Parser generators actually have a structure quite similar to the execution environment. The grammar file is tokenized by Alexa, then the parser creates an ST. Finally, generator outputs the parser. This is a parser generators work. Next, I explain some terminology related to language processing system. First, let's talk about formal language. Formal language is a field of linguistics that deals with language is a language in a mathematical and theoretical way. It focuses on how a language can be represented as a set of text. In this context, we don't consider the meaning of text. We handle it purely in a formal sense. For example, in English, the language is primarily represented as sequences of alphabets, occasionally interspersed with spaces and sometimes mixed in with symbols like commas and periods. In formal language, a language is composed of symbols that mainly appear as words in the text. Grammar that arranges these symbols in ordered manner. Then next, let's discuss context-free grammar. Context-free grammar is a type of formal grammar used to represent context-free languages, which is a kind of formal language. The form that formal grammar you see on the slide refers to type. The language generated by of such grammars is called a complex-free language. This grammar can be interpreted by saying that a symbol rule can be represented by rule A, both A, B, C, dot, 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 arranged in this order, or by symbols D, E, F, dot, 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 arranged in this order. This notation is called background form, commonly abbreviated as DNF. The reason I'm discussing this is that the almost programming languages belongs to this category. But grammar of many languages is represented using BNF, and this notation is also used in the grammar files, which is the input of parser generator. In context-free grammars, there are two types of symbols. The first type is non-terminal symbol, which can be likened to paragraphs or sentences in English. They are symbols that can be replaced by other symbols. The second type is terminal symbols. They are actual input symbols that appear in the text, such as puppets or spaces and other characters. Let's look at some examples of context-free grammars. Here's the first example. BNF is typically reads from top to bottom. So in this example, number consists with 2 digits replaced side by side, and digit represents any single numeric character. So what language is this grammar represent? So the language represented by these two grammars be described as 2-digit integers ranging from 00 to 99. Typically, numbers don't start with a 0, but in this language, take it like 00 and 01 or something else, valid representations. Let's look at the next example, which gets a bit more mathematical. An expression is defined as 2 digits with a symbol for addition, subtraction, multiplication, and division in between. The definition of digit remains the same as in the previous example. So what language would this grammar represent? So this represents a language for 2-term arithmetic expressions with 1-digit integers, such as 1 plus 2 or 6 divided by 7. So here's the final example. It's a bit more complex, and as it is recursively uses the symbols that appear on the left side of the grammar within the grammar itself. This is a body notation in BNF. This means that an expression followed by plus digit also considered an expression, or that an expression enclosed in parentheses is also an expression. So what language would this grammar represent? It's quite difficult. So let's consider 2 concrete examples, starting with expression. You can choose any operation, but let's start with division for example. Let's remember that an expression can be enclosed in parentheses. So let's enclose left expression. And let's change the enclosed expression to an additional operation. Since it's getting a bit long, so let's simplify the expression to a digit. Now let's replace the digit with 2, 7, and 3. So as you might have gathered from this example, this language represents arithmetic expressions of 1-digit integers with not only 2 terms. By the way, the parsers process is essentially the reverse of this. Given an input like that example, after tokenization by the Alexa, it first converts to the number into 7 and 3 or 2 digits. And continuing, the first digit can be converted into examples. From that expression, digit can be transformed to another expression. And then an expression with parentheses becomes an expression without parentheses. Converting the division into an expression, bringing us back to the original expression. This process allows us to determine that the initial input is correct according to this grammar. Here's a summary of that I covered so far. The Lexicon parser analyzes the program and creates its data structures, and then source code is executed or compiled. And a program which generates a parser from the grammar file is called Parser Generator. The input grammar file of Parser Generator is written in CFG, context-free grammars, and BMF is one of the representation of context-free grammar. Next, I talk about my contributions to Lrama. To summarize my contribution in a single point, it would be implementing named references to Lrama. However, this brief description might not fully convey the impact, so let me explain in more detail. Lrama is a Ruby-based parser generator, initially developed as the replacement for Bison. Lrama is pronounced the same as Llama, Yama, I don't know, for animals. You can find it repository on GitHub, the URL. The creator Yuichiro Kaneko is sitting over there. And Lrama is introducing at RubyKaigi 2023 by him. And the presentation video is available on YouTube. It's already being used in the build process for Series 3.3. So therefore, anyone here can try it out by building the head of Series now. The parser generator, parser generated by Lrama operates during the runtime in Ruby, but it doesn't change Ruby's behavior. So think of Lrama during the build process. Lrama is currently in its version 0.5 series for aimed at Series 3.3. With the release of release candidate of 3.3, this series has reached a milestone. So the development for 0.6 series targeting Series 3.4 has started. There are several benefits to creating Lrama, but when I asked Kaneko-san, he mentioned that the biggest advantage is not having to worry that the Bison bug. The Bison is a family, so it's a library used during the Ruby build process. Therefore, it is necessary to consider version of Bison installed the PC being used for the build. Even if newer versions of Bison have useful features, they couldn't be utilized if the install version was outdated. Additionally, implementing parser generator in-house has made it much easier to add Ruby-specific features compared to submitting patches to Bison. Not only can new features from Bison be implemented, but it's also now possible to incorporate features that Bison doesn't have. For example, nowadays, there's a language server protocol, LSP. It's only natural to want to pass even incomplete work in progress or to aid in making suggestions. Additionally, you might have heard that series pass-by has become overly complex and difficult to maintain. With the own parser generator like Lrama, we can absorb this complexity at generator level, making making code more manageable and easier to read. A recent example of Ruby-specific feature implemented in Lrama is parameterizing loop. This feature addresses the issue where represented list of arbitrary numbers of symbols or an optional symbol can be somewhat verbose with traditional BNF notation. It introduces a syntax trigger that allows for the expression of these concepts by appending certain symbols at the end of the original symbol. For instance, appending an asterisk to a symbol indicates that it represents at least of 0 or more occasions of that symbol. Typically, a plus sign signifies the one or more occasion occurrences, and the question mark denotes that the symbol may or may not appear. Finally, let's briefly talk on other parsers and parser generators related to Ruby. First, there's Prism. It is called up until this September. Like Lrama, Prism aims to replace CRuby's parser. However, unlike Lrama, which replaced Bison, Prism is a project that attempts to directly replace parser in CRuby with a handwritten one. Starting with CRuby 3.3, it is also provided as a default gem. Additionally, Prism is compatible with JRuby and Ruby, ensuring broader applicability across different Ruby environments. Next, let's discuss Bison, which was used in CRuby before Lrama. Bison is a parser generator developed by GNU as an improved version of an earlier parser generator called yui-knk. In CRuby, Bison was used to read parse_by and output the Ruby parser. Lastly, when it comes to parser generators in Ruby, RuBConf, which has been around for quite some time. RuBConf is not used in the core of CRuby, but is utilized in other contexts. For instance, the parser gem, which RubyConf depends on, uses RuBConf to generate its parser. You might wonder if RuBConf could have replaced Bison in the Ruby context. Both are the parser generators, and their underlying generation algorithm are similar. However, creating a new tool was more feasible due to some reasons. Firstly, consider the input file. As I mentioned earlier in this slide, Bison is an improved version of yui-knk, so it uses a similar format for input files. On the other hand, RuBConf is a Ruby-specific parser generator, so it incorporates various unique features in the grammar file format, leading it to incompatibility between the two. Moreover, there's difference in the language of parsers they generate. While Bison can output parsers written in C, C++, and Java, RuBConf generates parser in Ruby. In essence, RuBConf and Bison differ both in their inputs and outputs. To replace Bison with RuBConf, one could need to implement compatibility for both aspects, which present significant challenges. Moving on, let's discuss name references. Name references is a feature available by Bison, which allows for referencing of symbols or names within actions. So since I've introduced some new words, let me explain them. To understand named references, it's helpful to understand with the structure of Bison grammar file. Generally, a Bison grammar file consists these 4 sections. As a reference, I've included in parentheses to approximate number of lines for each section in C Ruby pass-by. 8 lines. You notice that it's quite expensive. Let's focus on the grammar file section, the grammar rule section. So, grammar rule section is where you write the grammar file of the language you want to pass. You can use DNF as I explained earlier to describe the grammar and font the language's grammatical structure. After each grammar rule, you can write an action, which is closed in braces. This talk today focuses on this particular part. By default, a parser generated by Bison only checks if the input text is grammatically correct according to the given grammar. If it doesn't, on its own, perform tasks such as creating ASD or save any operations necessary for subsequent. This is the same for Lrama. To address this, Bison allows you to write all braces after each rule. This code specifies what actions should be taken when an input is correctly parsed according to the grammar. These actions are embedded in the grammar generated parser and executed during parsing. This is what we refer to as action. Within an action, you can use dollar signs or atomic symbols to access the values of symbols in the rule. Called references. When significantly contrasting with named references, they are referred to as numbered references. Here's an example. As you can see, it's a grammar for an addition expression. The return value when this grammar is accepted is the sum of the first and third error. So let's discuss named references. First, I'll explain the issues with numbered references. Numbered references is simply use numbers to indicate the position of symbols, which can make it difficult to understand what values are being referred to, leading to lower reliability. Moreover, if the grammar changes, it must be rewritten since it signifies by position number. So named references were developed to address these issues. Instead of using numbers to identify the location of root value, you can use simple names. This enhances clarity and reduces maintenance burden associated with grammar modification. I want an example of converting numbered references to named references. As shown in the slide, within the action, you can reference the values by writing the symbol name with dollar sign, just like within numbered references. Additionally, in the grammar description, you can enclose the symbol name in brackets to assign it an alias. This is necessary when the same symbol appears more than once in the grammar. Otherwise, it will result in an error during parser generation. Moreover, you can use characters like hyphens or dots in aliases. Such cases, these aliases also need to be enclosed in brackets on the action side. Looking at this way, what do you think? Doesn't the bottom example seem more readable than the top one? In summary, my contribution to Lrama was the implementation of named references. Lrama is a parser generator built with Ruby as replacement of Bison. Named references is a feature of Bison, allowing the use of symbol names as references within action. I talk about internal structure of Llama as related to the action implementation process. Let's visit the topic of the internal structure of Parser Generators. Here's a diagram we saw earlier. Essentially, a Parser generator takes the grammar file, then let's say tokenizes it, and parser to present and see, and finally the generator produces the output parser file. When I delved into the code for contributing, I found that Llama's internal structure appears to this principle. Have classes the lexer, parser, and output, each having their respective roles in the process. After a preliminary review of this code, I formulated an implementation approach. At the point when I decided to implementation named references, number references were in press. So this meant that I could think that I could link the references with actions to the respective symbols in the grammar. The part of the code that automatically generates the related code could be reused. Moreover, the codes for tracing positions in the grammar and establishing links were implemented for a number of references. I saw that by referencing this, I couldn't implement the new code to trace symbol names and establish the corresponding links. Once the approach was determined, I started by writing tests. There were test cases to check whether the expected links were being established when grammar files using named references were processed. This step ensures that the new feature behaved as intended. So all that remained was the implementation. Considering the roles of letter, parser, and output, which file should be modified. As mentioned earlier, the letter was letter tokenizes the source code, and parser generates an SD, and output generates the parser. So initially, I thought that implementing the new code in the parser would be the right approach. However, it turned out this approach was correct. In reality, it was necessary to edit the lecture, not the parser. The reason why editing the lecture was necessary was Llama's design philosophy. In Llama, the lecture already had context of parsing, that is, information about what it was currently parsing. Moreover, when a lecture tokenized actions, it also established the associations of which symbols are being referenced. Moving all this implementation to the part would have been a considerable task and would align with the original design. Therefore, I decided to edit the lecture. So the reason why the lecture holds the context for parsing is not just the parser, but the lecture too. Needs for context proper functioning. For instance, source code written within comments should be treated the same way as lecture code. It's typically ignored. Or, and reading header, the lecture must continue tokenizing without interruption, even if unexpected line breaks occur within words. This requires the lecture to be aware of context, like inside a comment or inside a header. In essence, both the parser and the lecture require contextual information. This question becomes, which is more appropriate press to hold this context. The choice whether the lexer or parser should hold the context has its pros and cons, and there isn't one size fits all answer. If the lexer holds the context, it can tokenize everything in one go, changing its state as needed, and pass the token to the parser. This approach separates tokenizing parsing into distinct phases, which is design philosophy behind Gamma. On the other hand, if the parser holds the context, it can refer to its own state and request appropriate tokens from the lexer. The advantage here is the lexer only needs to focus on tokenization. The slide only mentions the advantage, but the side of both is similar and straightforward. The complexity of code increases as the holding the state becomes more intricate. After successfully implemented the feature, I submitted a pull request and merged. So in terms of feature applications, yeah, I'm currently interested in implementing a parser generator for the IE-error algorithm. This is an improved version of the LALR algorithm, which current Yama generated parser use. The IE-error algorithm was introduced in the published in 2009, and it has already been implemented in Bison. So this concludes my presentation. I found development of parser generators extremely fascinating and rewarding. I hope that my talk has sparked interest at least a few of you. Thank you so much for your attention.
Thank you so much for your sharing. Do anyone have a question for him?
So much for your helpful talk. I'm interested, since you're involved at least somewhat in the Llama parser. We seem to have two efforts going on that are quite active, Llama and Prism. I'm wondering, they're both featuring in Ruby releases. And I'm wondering what you think is the future between these approaches and how they might relate to each other as time goes on.
So I don't know the future, but I'm contributing Lrama. So so I want to win the battle by Lrama.
Thank you for your answer. Do anyone have any question now?
So, sorry, this is a good question, but I see that the Llama LRAMA is also written Ruby. So, isn't it like a weird thing that we use Ruby to the parse.y? Isn't it like
猫さん、今の質問わかります I'm a also from Lrama. I want to answer the question. So he says the Lrama itself is written by a Ruby. However, it was used to generate the RT file, which is the block component Ruby's parser. So yeah, it's a problem. So however, Ruby in build process requires another Ruby. We call the computer code is a base Ruby. So there are no problem of the boot. We expect or we are we our assumption that when you build the C Ruby, you already install kind of older version of Ruby on your so we can use it in the and when we provide the it for you in the release field of the C3, the first file is already created in the process and the package included. There are no problem.
Thank you for your question and thank you for your answer. This is thank you so much. Thank you so much. Kobayashi, thank you so much.
Thank you.
Okay, I ask a quick question. Like anyone, like, do you know that tonight we have like official party? Do you gonna join that? Can you raise your hand if you join that? Okay. Oh yeah, thank you so much. I just want to count like how many of you gonna join that. Thank you so much. Also, we're gonna have like a few minute break, and we're gonna go to next our last speaker today. Thank you so much.